So for this problem, we have another at least one situation. And if you remember our work from last week, remember you find the probability of none, right? Find the probability of 0 defects, and then we're going to subtract that from 1. So I was thinking, why can't we just do what we did last week? If every trial is independent and the percent won't change. So to find the probability of no defects, I did 1 minus 4%, or 100 minus 4%, got 96 and made it a decimal. And then since I'm looking at 5 of them, what's the probability at least 5 won't be defective? So I went 0.96 to the 5th power, got that number. So that number is the probability that there are no defects. So if I subtract 1, that'll add up, that'll find all the other remaining probabilities. Probability of 1 defect, 2 defects, 3 defects, 4 defects, or all 5 are defective, because that's what we're interested in finding out. And notice that did take that answer. So then how does this relate, so to just show there's some overlap, how does this relate to a binomial distribution? Because is this a binomial experiment? Well, there are fixed number trials, there's 5. The probability, there's only 2 outcomes, right? It's either defective or it's not. I'm assuming that there's no relationship, or the trials are independent. So just because one randomly selected item is defective doesn't mean the next one will be. I mean, maybe that's a bit of a stretch, because if there's something wrong with the machine, they're all coming off the same machine. But that's another story. And then the probability is the same. So it is a binomial trial, binomial experiment, Bernoulli trial. So I typed in that binomial calculator, I put probability of success. In this case, a success is finding a defective part. There's 5 trials. I'm interested in having 0 defectives. Notice it's the same number. And then if we take that away from 1, we'll get that. So your choice on what you do. Doesn't matter.